So last week we saw this Radon-Nikodym derivative theorem, and let's just recall. We have, if you have some measure, let's call it nu, is absolutely continuous with respect to another one, and they're both sigma finite. Well then, the smaller one, this nu of v, is going to be equals to the integral of some function. Let's call it f d mu for some f. Okay, so for here the usual notation is we write f to be we write d mu on top and the d mu at the bottom. Okay. So one way to think about it is sometime we will write the nu is just basically equals to d mu over d mu times the mu. Okay, you can think about it as a change of variable formula. All right, so let's just in this video we're just going over some of these basic properties of the Radon-Nikodym derivative. Okay, so the first corollary we're going to look at is that this derivative not only gives us a way to measure the new measure, but also tell us how we integrate respect to the new measure. Okay, so in fact, we have, if I want to integrate some g of the nu, okay, so here nu is absolutely continuous with respect to mu, then what I can do is I can write this as an integral respect to the mu measure, but I need to do something like a change of variable formula. I need to multiply the derivative here. Okay, so looks like as if this mu and this d mu and the d mu over there get cancelled, and you end up with d nu. Okay, so that's kind of the idea behind this formula. Okay. The proof is fairly simple, so this is probably you already seen it on your assignment. So to show these kind of integral are the same for all measurable function g, so you start with assuming g is equal to some characteristic function. Then the integral of the characteristic function on one side is just the nu of the measure of this set. Okay, we already know this is just the integral of, if I write it this way, the chi of v times the Radon-Nikodym derivative, and let's just write it like that. And so basically this is the function g. Okay, so for characteristic function, this equality holds, and you can say by the integral is linear. This will hold for all simple functions. So this also holds when g is greater than or equal to 0 and g is simple. Okay, you just do a finite linear combination of them, and that still holds. And the rest of them, so if you have in general, so if your g is greater than or equal to 0, then you just pick a increasing chain of simple functions. Simple. And let's just assume for now the nu and mu are just positive measures, so your Radon-Nikodym derivative is also positive. Okay, we'll talk about the sign measure later, but so you will have a sequence of simple functions that converge pointwisely to your g, and these are non-negative as well. And moreover, if you want to multiply by the Radon-Nikodym derivative, so this, if you multiply a non-negative function, so let's assume mu and nu are positive measure, you still have an increasing sequence of functions that converge to g of d nu over d mu. Okay, so you have these two convergence. Okay, and so you apply MCT. Okay, so apply MCT, and it should extend to this function g. Okay, so you can finish when g is non-negative measurable, and then you just, for any g in L1, you do the positive negative part, and this should finish the proof. Okay, and when nu is a sign measure, okay, that's going to be really similar proof. I would just leave it as an exercise. You can try it on your own. All right, so the next little example or corollary, you can depend on how you see it, is the following. So if you have a sign measure, let's say nu is a sign measure, let's assume this is the nu absolute value is sigma finite. All right, then one thing what you can show is that the nu is actually absolutely continuous with respect to its absolute value. Okay, so why is that? Okay, so this is quite simple. So proof. So if you have something that's equals to, it's a null set for the absolute value of this nu. Okay, so if that's equal to 0, so recall the absolute value is basically you do the Jordan decomposition. You have a positive part and you have a negative part, and you sum them up, you get the absolute value, so that's going to be 0. And that just simply implies because now the positive part and the negative part, they are both positive measures, so the nu plus and nu minus of E are both going to be equal to 0. Okay, so that's the only way you can have their sum is again equal to 0. All right, so that just implies the nu of E is equal to 0. Okay, so that's really easy. Okay, so Radon-Nikodym derivative tells you that, so the Radon-Nikodym tells you the nu of a set E is just equals to the integral of some, let's say H, integrate over E of D of the absolute value of nu, okay? So this is basically the Radon-Nikodym derivative tells us. Well, in fact, we can know a little bit more about this H, okay? So in fact, I want to tell you what this H is, okay? So in fact, so H is basically the following. So remember this, the nu has a high decomposition. So you decompose the positive part and the negative part of the space, okay? You partition it in a almost unique way. And you let H be the characteristic function over the positive part. So you want it to take the positive one on that. And on the negative part, you want to take the negative one. So you minus the characteristic function on n, okay? So in fact, this is a Radon-Nikodym derivative. And by the uniqueness of high decomposition, if you have another P and then you get a different one, but they are only differ by a null set, okay? So that's unique almost everywhere. Okay, so let's try to just show explicitly why this is the case, okay? So on one hand, you have the nu of E, okay? So you can break it into the positive part, so the nu intersect P. And you also break it into the negative part, the nu intersect N. All right, on the positive part, this is no other than the positive nu plus, because that's where the nu plus is concentrated on. Okay, that's supported on this part. Okay, so the nu plus and nu agree on any subset of P. And on the other side, on the N part, you have this nu is actually the negative of the nu minus of E intersect N. Okay, so this is because nu minus is a positive measure, so on that part, the nu takes the minus of nu minus. All right, and we write these as integrals. So this is the integral of E intersect P of the characteristic function. I just use 1 of d nu plus. And you do the integral of the E intersect N of 1, or actually it should be the negative 1 of the d nu minus, okay? And because the nu plus, if you restrict to n, is going to be 0, and similarly the nu minus restricted to the positive part should be 0. So because of that, you can just replace this nu plus and nu minus by the absolute value of nu, okay? So it's really just because it's all null set for them on any subset of P or N, okay? So this one just equals to the integral of E intersect P of the, let's say, one function of the absolute mu, and plus the E intersect N of the negative one of the absolute mu. And now it's fairly simple to see this is just if you just want to write it as integral over E, then on those sets inside E intersect P, you take the positive one. So you say characteristic on P, that's positive one. But when it's on N, it's negative one. So you minus characteristic on N. Okay, so this is D of mu. And now you show that this is essentially what you expect it to be. Okay, so we kind of explicitly showed how this, considering the sign measure nu and its absolute value, how this H, this Radon-Nikodym derivative looks like. Okay. All right, I just want to conclude this lecture with some nice properties of these Radon-Nikodym derivatives. So here's a proposition. So suppose I have some, let's say lambda, nu, mu, and lambda. They're just all sigma finite measures. And so suppose, first of all, if I have nu and lambda, they're both absolutely continuous with respect to, I should change this notation. Let's say nu and nu, both absolutely continuous with respect to lambda. Okay, then what we can do is we can take their sum. So for example, I can take their sum. That's going to be absolutely continuous to lambda as well. And if I have any scalar, let's say C is a non-negative scalar, then I can scale the one of my mu, and it's still going to be absolutely continuous with respect to lambda. Okay, that's not surprising, and moreover, if I want to talk about their Radon-Nikodym derivative, okay, so now because the sum and the scalar multiple are still absolutely continuous with respect to lambda, so I can consider the Radon-Nikodym derivative of their sum with respect to lambda, and I can consider the multiple of mu respect to lambda, okay? They're just going to be what you expect them to be. So in the first one, when you take the sum, the Radon-Nikodym of the sum is just the sum of their Radon-Nikodym derivative. Okay, so this is just going to be the sum. This should be a nu here. So d mu d lambda. Okay, so of course this is almost everywhere lambda. And the second one, you can pull out the scalar is c times the d mu over d lambda. That's almost everywhere lambda. Okay. Why this is the case? Well, let's just prove the linear part, and I'll leave the other one as exercise. So it's really simple because you just write basically the definition, and we already proved all the heavy lifting stuff. The uniqueness part is done in the Radon-Nikodym already. Okay, so let's just consider if you have mu plus nu of some set E, okay? So by the definition of the Radon-Nikodym derivative, so this is equals to the derivative d mu plus nu over d lambda times d lambda. Okay, so this is the function, the Radon-Nikodym function. I just write it this way. Okay. Well, but on the other hand, this is no other than the mu of E plus the nu of E. So you do the Radon-Nikodym for these two again. So this is the integral of the d mu over d lambda plus the integral of E of d mu over d lambda, integrate respect to lambda. And you can write these integral, these two are just functions, okay? So even though it looks like d over d is still a function, so you can just group them together, okay? So this is d mu over d lambda plus d nu over d lambda times d lambda, okay? So basically, what we prove is now is if you consider these lambda plus nu of E, there are two ways of writing it as an integral of some function. One, of course, is just the Radon-Nikodym derivative, so this is one. And the second is written as the sum of these two. And the hard part is already done by our Radon-Nikodym derivative. So one has to equal to almost everywhere. Okay, this is just part of the uniqueness part of the derivative, and so we're done. Okay. All right, so I want to prove the second property I want to say is suppose you have some mu which is absolutely continuous with respect to mu, and your mu is absolutely continuous with respect to lambda. Okay, so this absolute continuity is kind of transitive. Okay, so you will imply the nu is going to be absolutely continuous with respect to lambda as well. And moreover, if you consider the d lambda over d nu, okay, so that's going to be, well, you can have some kind of change of variable formula again. So you do the d lambda over d mu here, and then you do the d mu over d nu, okay? So they are going to be the same almost everywhere lambda, okay? I think I write it the other way. Okay, let me just erase this. I should have said if I want to consider d mu over d lambda, okay, that's going to be d nu over d mu and d mu over d lambda. Okay, that's the correct way. Okay, so that's almost everywhere lambda. Okay, so it looks as if you're trying just to cancel this d mu and d mu here, okay? So just as if what's happening here. All right, the proof is really the same. You just consider any measurable set E and you measure how is you consider nu of E and you write as integral respect to mu first, and then you do it again. You get to integral in terms of lambda, and again you apply the uniqueness there. Okay. All right, and thirdly, what I have, because I have this transitivity, so I can think about when those measures are absolutely continuous with respect to each other. So this is, suppose I have mu is absolutely continuous with respect to mu, and mu is absolutely continuous with respect to nu. Then what will happen is, well, if you think what will happen is the following. So if I have consider the first one, I can consider because nu is smaller than nu is smaller than mu, so I have a rather Nicotin derivative of nu respect to mu. And I can do the same for the other one, so I have d mu over d mu, okay? So this, what it looks like, it should look like, based on the theorem we just proved the part 2, it should be equals to d mu over d mu, but you can think about d mu over d mu, you're not changing any variable, okay? So it should be just 1, okay? The constant 1 function, okay? So this is what we're claiming, okay? This is going to be equals to 1 almost everywhere, mu, okay?